So let's look at an example. I'm going to look at exercise 1.2 on the tutorial sheet. We're going to prove that L2, that is the set of all strings of zeros of length p, where p is any prime number, is not a context-free language. So let's go through the proof. So first, we're going to assume that L2 is context-free. Is a context-free language, okay? So that means the pumping lemma applies, right? So necessarily there has to exist some natural number such that for all z in the language, where z is at least as long as n, pumping lemma applies. Okay, what we have to do now is we're going to choose some string in the language, at least as long as n, so we can start to decompose it. So I'm going to choose the string. Z is 0 to the p, where p is the nth prime number. And there's infinitely many prime numbers, so I can always choose a p that's the nth prime. Note that p is greater than n because the primes are a subset of the natural numbers. They have to grow faster, right? If there were more primes, if p was less than n, that would mean there are more primes less than 10 under 10, and you get like a contradiction. That can't be, right? Okay, so we have some length of primes. So now there exists some decomposition, so we have to show for any decomposition it fails. So we're going to decompose z as some arbitrary decomposition. Okay, so all of these strings are just going to be some number of zeros because z itself is just some number of zeros. So we're just going to label them all. I, j, k many zeros, l many zeros, and I don't want to use m because I'm going to use m over here, so I can't use n either. I can't use p, I'll use q. I'm running out of letters here. Okay, there we go. So such for any decomposition, these three properties hold. So these three properties hold. What does that tell us here? So it tells us VWX is less than or equal to n. So that tells us j plus k plus l is less than or equal to n. We get that from the first property. Vx is non-empty, so that means j plus l is at least 1. And what's this property here? So it tells us for any m greater than 0, this string here is still in the language. And what kind of strings in the language? Strings of zeros of prime length. So it tells us I plus m many lots of j plus k plus m many lots of l plus q is prime. And this is true for every m. So what we've got to do now is we've got to choose some m's such that this thing isn't prime and get a contradiction. So if you notice, you can sort of group the j and the l together. So this thing's the same as m j plus l plus I plus k plus q. Okay? So what m can I choose such that I can show this thing is not prime? Or what does it mean to be not prime? It means you're composite. That is, I can sort of factor you into two smaller parts, where both of those parts are at least 2, right? Because I can write 7 as 7 lots of 1. So to be a true factorization, both the factors have to be 2 or bigger. So if I choose m is equal to I plus k plus q, then this term here becomes I plus k plus q times j plus l plus I plus k plus q. So this is j plus l many lots of I plus k plus q, and this is 1 many lots of I plus k plus q. So we can combine these terms. I plus k plus q, j plus l plus 1. Okay, so we've factorized it, but we're still going to check that both factors are at least 2, right? So this property here, j plus l is at least 1, tells us j plus l plus 1 is at least 2. Okay, so this half of it is at least big enough. Now we need to show I plus k plus q is at least big enough. And how can I do that? Well, this has to work for all m, right? For all m, this term here has to be prime. So what happens if I choose 0? If I choose 0, these two terms fall away and I'm just left with I plus k plus q. So if we choose m equals 0, I plus k plus q is prime. Okay, and if it's prime, well, the smallest prime there is 2. So that means I plus k plus q has to be 2 or bigger, right? Which means this term here is also bigger than or equal to 2. And so I have a legitimate factorization. So therefore, not prime, which is a contradiction, because it contradicts the pumping lemma for context-free languages.